And welcome back. As we kind of wrap up our review, our next topic is trigonometric functions. And we're going to start this conversation off by reviewing radian measures. And radian measures are simply the angle ACB that's at the center of a unit circle, which is equal to the length of the arc that ACB is cutting from that unit circle. And so let's look at this best with an example. So we want to start off first by finding the arc length. So we want to find the arc length here on a circle. Let's say the length of arc subtended on a circle of radius 3 by a central angle of measure 2 pi over 3. So the best way to think about this is, okay, well, how do we want to approach this? Well, let's use, in this case, a variable to represent the subtended value. So just say s. And this is going to be equal to our radius times theta. Now, theta, of course, is the measurement of the angle, and we have already been given that as 2 pi over 3, and our radius is 3, so we can just go ahead and plug in these values. So this is going to be 3 times 2 pi over 3, and with some very simple math here, we know that these 3's are going to cancel, so our s should equal simply just 2 pi. And this is going to be a good lead-in for what we want to talk about today, which is, of course, our trigonometric functions. When we have an angle of measure theta placed in a standard position at the corner of a circle radius r, we get the 6 basic trigonometric functions. So we have sine, cosine, tangent, cosecant, secant, and cotangent. And you can see with each of these have their own unique relationship between x and y here. And when we graph these functions, of course, we are going to get some very familiar graphs if you recall previously. So if we stick these in the coordinate plane, we are actually going to denote our radians with the value x instead of theta. Which is a very common substitution. So f of x will equal sine of x, f of x equals cosine x. Here is our cosecant of x, as you can see, and our secant and our tangent and cotangent. And of course, you'll note in here we have our intervals set to values of, in this representation at least, pi over 2 for all of these. And you can see that we have period values in here. And that is a good thing to kind of note here because that's a good jumping point to our next topic. So periodicity is when an angle of a measure theta and an angle of measure 2 pi plus theta are in the same standard position, their terminal rays are going to coincide. The two angles therefore have the same trigonometric function values, such as cosine of theta plus 2 pi equals cosine theta. This is why when we look at things like the unit circle, why those values, even if we go past 2 pi, are able to kind of repeat in what those evaluate to. Now this is not simply just limited to cosine. This applies to each of the trigonometric functions, and the same behavior applies to values of 0 or theta minus 2 pi. Because, whether you're going clockwise or counterclockwise on the unit circle, you're going to have that same value come out if you're using 2 pi. Now, the values of trigonometric functions repeat at regular intervals, described as periodic intervals. And so a function f of x is periodic if there is a positive number p, such as the function x plus p is equal to f of x for every value x. And the smallest value of p is what we define as the period of f. Again, looking back at that previous example with those visual representations of graphs, we saw that we had pi as the period for tangent and cotangent, whereas we had the value of 2 pi for sine, cosine, cosecant, and secant. And again, that's noted right here. So sine, cosine, cosecant, and secant are all periodic with an interval of 2 pi, while tangent and cotangent are all periodic with an interval of pi. Now, a quick note with this is that when we start talking about these functions, when we talk about even and odd trigonometric functions, if we look back at those graphs, we can look and see that, cosine and secant are both even functions. All right, because what's our definition of even function is that they can kind of fold, right? Whereas the others are all odd because what is it? They have symmetry around the origin. So again, important things to kind of keep in mind here that only cosine and secant, if you have to know what those are even functions, all the others are odd. So with all that in mind, let's actually go ahead and try to find some trigonometric values. And what we want to do here is find all the trigonometric values of theta if sine of theta is equal to negative 3 over 5 and tangent of theta is less than 0. All right, so the way we want to evaluate this is first we have to think, okay, where is theta at? Well, if we were to actually take and look at this, okay, so we have a negative value of sine, and we know that theta has to be less than 0. If we were to go ahead and map that out, and we look at our different quadrants that the unit circle inhabits here, we are going to find that this value can only exist here in the fourth quadrant. And because it's in the fourth quadrant, the reason why we know that is because this is negative and this has to be negative. And if you remember with tangent is another way of thinking of this is sine over cosine. And we know that sine is negative, and this has to be a positive value in order for tangent to be a negative value. So that's why we know this has to be quadrant 4. So let's go ahead and think about, from this then, what do we have to do to get all the other trigonometric values? So we already know what sine of theta is, right? Sine of theta is negative 3/5. So let's go ahead and determine then, okay, well, if this is negative 3/5, what is going to be, for example, our cosine value? So cosine of theta, well, if we look at this, this is 3 and 5. If you think back to basic geometry, one of our special right triangles is the 3, 4, 5 triangle. And if we know that this is a 3 and 5, then this has to be 4/5. And because we know that this is a sine over cosine relationship, what's going to be our value for tangent of theta? Well, our value for tangent theta is simply going to take these two values. The 5's will cancel out, so we're going to end up with our negative 3 over 4. And so that is our tangent of theta. Now to find our inverse functions, it's pretty easy to do those because remember with the inverse functions, you're simply just interchanging those values. So if I want to do the cosecant of theta, I'm simply going to look at what my sine value is here, and I'm simply going to flip these over. So this is going to be a negative 5/3. If I want to know what my secant value is, again, look here at my cosine, and I'm going to flip that over to 5/4. And if I want to know what my cotangent value of theta, I'm going to look here at my tangent, and I'm going to flip that over to 4 over negative 3. Now, this is a very easy approach for a lot of this, but what if we start dealing with transformations? Because obviously not everything is going to be simply just sine, cosine, tangent. A lot of times you'll have other things that might modify it. While the rules for shifting, stretching, shrinking, and reflecting the graph of function apply the same way to trigonometric functions as we would to others. Now, the general sine function or sinusoid can be written as follows. So f of x equals a sine bracket b parentheses x minus c and parentheses plus d. All right. So this, of course, is getting us our function right here that we're going to evaluate. And if we want to pull apart these pieces here, if we say, okay, we have a, all right, what does a represent? Well, a is our amplitude, all right. That is, of course, the value that is our amplitude for the waves themselves. We have 2 pi over b, that is going to be our period. We have c, which is our horizontal shift, and then we have d, which is our vertical shift. And those are the different pieces that can actually affect things like shifting, stretching, shrinking, and reflection. So with that in mind, let's apply this to an example. We want to determine the period, the domain, the range, and then the graph of the function y equals 3 cosine of parentheses 2x minus pi and parentheses plus 1. All right, so let's just pull the different pieces apart here. If we look at this function here, remember we want first the period. Well, the period for part A we define as 2 pi over b. All right, so if we look at 2 pi over b, we can take this function here and say, all right, we have 2x minus pi. Well, this doesn't really help us because it's not in that general form. So let's just rewrite this function here. Instead of being y equals 3 cosine parentheses 2x minus pi, we want to put that in a form where it's b parentheses x minus c. All right, so let's go ahead and rewrite this as y equals 3 cosine. And this will be my square brackets here. And now we need our b value. Well, the b is simply going to be this 2 that we pull out, parentheses, x minus pi over 2 plus 1. And so that is going to help us if we need to pull out any of the other information. Now, this, of course, is not going to really change too much with our period, but if we needed to find other pieces of this, this is where this is going to come really useful. So going back to our 2 pi over b, we can look right here and say, oh, what's b? B is right here. It's 2. So I have to do 2 pi over 2, which means that my period is simply going to be pi. All right, what about the domain of this function? All right, well, if we look at our function, what do we have? We have cosine. So the value for cosine means that my domain is going to go from negative infinity to infinity. And the range of this function is going to depend upon our other factors that we have in here. Now, it is a basic cosine function. Remember, the basic cosine function is simply going to have a range from plus or minus 1. However, because we have an amplitude right here, we have an amplitude, and we also have a shift, we're going to have to use those and factor them into this. So again, remember our basic cosine function is going to go from negative 1 to 1. So what we have to do is take this value of negative 1 to 1. So negative 1 to 1. And first thing we do is, okay, we look at our amplitude. Amplitude means that we're multiplying. So I'm going to multiply each of these by 3. So multiply by 3, which means then we're going to have a value that's going to go from negative 3 to positive 3. But then notice that we also have a shift up of 1 unit. So it means I have to add 1 into here. So now my final value for this means that this range is not going to go from negative 1 to 1, but instead is going to live at negative 2, because remember this is a negative 3, to a positive 4. And that should give us our actual value that we need for the range. Now, if we want to see the graph of this function, we of course could draw it, or we can also use our calculator here. So I'm just going to go here, clear out the existing stuff I have in, and I'm going to go ahead and plot this in. So 3 cosine. I'm going to use my original function here for this graphing purpose because it'll just be a little bit easier. 2x minus, and let's do pi, and then we have to do plus 1. And for this purpose, we can go to our zoom. We have, of course, a trigonometric one, so let's go ahead and see that one. And you can see here is our function that we have created. So if I needed to sketch this, I would have a good reference here that I can use to sketch this graph of 3 cosine parentheses 2x minus pi plus 1. All right, let's apply this again now with another example. Let's find the frequency of a musical note. So in this example, a computer analyzes the pressure displacement versus time for the wave produced by a tuning fork and gives this equation as y equals 0.6 sine parentheses 2488.6 x minus 2.832 and parentheses plus 0.266. And what we want to do with this is estimate the frequency of the note produced by the tuning fork. Now, again, this is going to go back to using that kind of standard form that we are expecting. Now, in here we can rewrite this equation, but remember when we do this, we're a lot of times just pulling out this piece right here. And when we look at this, it's effectively saying, what is the period of this? Well, period, if you remember, is 2 pi over b. And that's going to give us a good starting point here, because now we can take and pull in this b value. So this is going to turn into 2 pi divided by 2,488.6. Now, while this is the period, what we're actually interested is in the frequency. So we actually have to flip this whole thing here. So we're actually going to flip that over and change that to 2,488.6 divided by 2 pi. And I can't do that kind of calculation in my head, so I'm going to actually use my calculator to help me out. So let's go ahead and plug that in, 248.6, and divide that out by 2 pi. All right, and we get about 396. I'm just going to go ahead and just leave that as a whole value here. So let's go ahead and approximate it out to 396. And because it's wanting frequency, we can put this in a unit measurement of hertz. Now, of course, this is not necessarily the exact same calculation as you would have on a temperate scale, but this is what we're looking for this scenario. Now, we've already seen these a little bit here, but we need, of course, to discuss inverse trigonometric functions. Now, none of the 6 trig functions that we've looked at are one-to-one. All right, they're just not. All right, if you draw that horizontal line test, they're going to fail. However, though, if we restrict the domain of those functions, we can find a new function that does have the inverse. So, for example, when I take if I want an inverse of cosine, I can restrict the domain between -1 and 1, and my range will then be between 0 and pi. Similarly, if I do sine and want an inverse sine, again, between -1 and 1, and my range is going to be between -pi/2 and pi/2. For an inverse tangent, we're going to be between -infinity and infinity, and our range will be between -pi/2 and pi/2. For a inverse secant function, I can do a absolute value of x is greater than 1, and for my range, we're going to be between 0 and pi, but notice that y, in this case, cannot be pi/2, and that's because we have asymptotes to deal with. When we have a inverse cosecant, you can see I have the absolute value of x again is greater than 1, and we're going this time between a -pi/2 to pi/2 with y cannot being at 0. And when we have a inverse cotangent, again, you'll see we go from -infinity to infinity, same as the domain here for inverse tangent, but this time we're going between 0 and pi. And so when we actually take a look at those functions here, you can now see how those graphs are. So here is our inverse sine, here's our inverse cosine, our inverse tangent, our inverse cotangent. All right, so let's go ahead and apply this to find angles in both degrees and in radians. So here I want to find the measure of the inverse cosine of -0.5 in both degrees and in radians. Well, the easiest way for us to do this is, in this case, simply just grab our calculator. So I'm going to go ahead and plug in the inverse cosine of -0.5. First, I'm going to check my mode, though, so I see which one I'm currently in radians. So let's go ahead and do an inverse cosine of -0.5. And if I hit enter, I'm going to get a value here of 2.094. So that's a pretty good approximate value for us to work with. And now I'm just going to need my degree mode. So all I'm going to do is go back over to my calculator, change my mode back to degrees. Even though it's not something we use as often, we're going to go ahead and do that. And let's go ahead and use the same function here. But now if I hit enter, you'll see I get the value 120, which means that this is in degrees. So this is 120 degrees, whereas this is in radians. And lastly, let's go ahead and do a little bit of solving work here. So we want to use our inverse functions to solve for x. And I have 2 different pieces to use. So I have a sine of x is equal to 0.7 for between 0 is less than or equal to x, which is less than 2 pi. And tangent of x is equal to -2 for -infinity to infinity. So let's go ahead and start with part A here. All right, so for part A, we know we have the sine of x is equal to 0.7. So the simplest way for us to approach this is say, hey, you know what, let's go ahead and do an inverse of this. So we're going to go ahead and say that this is the inverse of 0.7. And we can go ahead and get a radian value here. So I'm going to go ahead and again go back to my calculator. Let's change my mode back to radians. And we're going to do an inverse sine of 0.7. I didn't hit the second key there, so let's go ahead and hit that. There we go, got an inverse sine now. 0.7, there we go. That's the value we want. And so now I have a value of 0.775, so approximately. So let's change that to an approximate. So 0.775. Now, the thing is, this is not necessarily the only solution in this interval, right? It's actually technically going over into a second interval and we're in that next interval because we are now moving from the first quadrant into the second quadrant. We need to apply a pi minus that initial value, so 0.775. And that should, of course, get us our new value. So let's just go ahead and just do pi minus 0.775. Actually, I can even make that more accurate by just doing minus second answer here, so we can make sure we get nice, good value. So we got 2.366. And so that's my two values that are going to be solutions for x. If you get at least this one, that's at least one solution. But remember, you do have to look for other solutions here when you start looking at where these values are, because remember, this value right here is saying it's between 0 and 2 pi, and our normal range of this is going from negative pi to pi. So again, very important that you check what that range is, because you may have to find a second value. So let's look at b then and see if we have something similar going on. So here I have the tangent of x is equal to negative 2. Now, just like before, we can set this up by saying, okay, what is the inverse tangent of negative 2? And again, I'm going to grab my calculator, and let's do a inverse tangent, and let's do negative 2. And I got the value of negative 1.107. Again, another approximation here. All right. And again, if we look at this interval, all right, we are saying, hey, this interval is possibly the only solution to this equation. Because remember, when we look at the inverse tangent, all right, the inverse tangent is going to operate between negative infinity and infinity. So in that case, we are pretty good here. However, keep in mind that tangent is periodic with the period pi, and because of that, the solutions to this equation, we actually need to write it into an equation form. So yes, this will give me a value, but the better way to think about this is that this is actually more like negative 1.107 plus our period. So we have some value, k, times pi. And you don't have to necessarily use k. You can use really any value you want. It's simply just going to represent an integer that is going to be whatever that interval is that you're passing through. But this should, of course, give you a little bit of a foundation here when we are doing our review for these various different pieces that you're going to need to know as we move forward into calculus.